Okay guys, let's go ahead and get to some limits at infinity, but I think it's important to go ahead and deal with the Algebra 2 and the pre-cal background to this particular topic because it's something that we actually went over both years. Now, if we have something like the limit as x approaches infinity, 3x squared minus 4 over x squared plus 2 or something like that. What question is that really asking? That's asking what happens to this. And of course, this expression right here stands in for the function f of x, or whatever you want to call it, okay? Now, because this stands in for a function, now we always have to remember that when we're talking about limits, limits are always questions about functions. And this question asks, what happens to this function when x gets really, really, really big? Well, that sounds like our old friend end behavior, okay? And if you remember, we had particular rules about determining end behavior, okay? Now, there is a particular way in which we are supposed to handle limits at infinity in a rigorous calculus sort of way, okay? But I don't want to do that in this video. In this video, I want to go back and I want to pull forward how we used to deal with them, okay? Because it's actually rather relevant. Now remember, if we were dealing with a function, a rational function, and we needed to deal with end behavior, we needed to remember that the end behavior asymptote, which I always abbreviated EBA, is always y is equal to the quotient. And some of you are going, oh yeah, I remember that. And then I said something that made a lot of you very, very happy. I said you don't always have to take the quotient to know the quotient, okay? And I distinguished three different types of rational functions, okay? Now, if I have something like y is equal to 2 over x plus 3, that is one where the degree of the numerator is less than the degree of the denominator, right? And when that is the case, just like the fraction 2/3, if I say how many times does 3 go into 2, well, it doesn't. 2/3 times, I guess. I mean, it just doesn't go in, right? So when I say how many times does x plus 3 go into 2, well, you don't actually have to take the quotient to know that x plus 3 doesn't go into 2. And therefore, the end behavior asymptote is y is equal to 0. Now, if we think about that numerically, it makes a whole lot of sense. Because when we're talking about end behavior, we're talking about things that get really, really big in terms of the input value. Well, as x gets really, really large, plug in 10. Then plug in 100, then plug in 1,000, then plug in 10,000, a million, a billion, keep going up. Well, that too is not changing. And therefore, as this denominator increases without bound, as this denominator goes towards infinity, it starts to dwarf that numerator. And while it never officially gets to 0, it approaches 0, okay? So anytime the degree of the numerator is less than the degree of the denominator, our end behavior asymptote is y is equal to 0, okay? Now the second one was y is equal to 2x over x plus 3. Well, in this particular scenario, the degree of the numerator is equal to the degree of the denominator. And when that's the case, you also do not have to take the quotient to know the quotient. Because you know that when you actually set up the polynomial long division, x plus 3 goes into 2x plus 0, how many times does x go into 2x? Well, it goes in twice, right? And so what happens, if the degrees are the same, you always get an end behavior asymptote of y is equal to the ratio of the leading coefficients. Okay? Coefficients. In this particular case, 2 over 1, right? 1 is the leading coefficient of the denominator. Now, the last one is, if we have one scenario where the degree of the numerator is less than, one where the degree of the numerator is equal to, we also have to have one where the degree of the numerator is greater than the degree of the denominator. And when that happens, we actually do have to take the quotient in order to know the quotient, right? So it's actually y is equal to the quotient. Now, this helps us, and I'll tell you why this helps us. There is a more rigorous way to do limits at infinity, to investigate what happens as x goes to infinity or negative infinity for a particular function. The great thing is that those questions, I can't remember if I've ever seen that question asked on a free response section of an AP exam. That means that any questions that come at you in terms of an AP exam are going to be in the multiple choice section. Well, in the multiple choice section, they don't exactly check how you did the problem. They simply give you credit if you got it right, and they don't give you credit if you got it wrong, okay? So let's go ahead and go back through how to evaluate some of these things just from our Algebra 2 and our pre-cal strategies, such that when we approach these things on an AP exam, we can do them as quickly as possible with as little time as possible, so we can save that time for the harder questions that we actually encounter. And in future videos, and I'll probably do 1 or 2 more videos, we actually will go through some of the problems and how they can be dealt with in terms of that more rigorous strategy. Now, let's go ahead and let me find my place real quick. Okay, so let's go ahead and say, well, let's look at the limit as x goes to infinity of 2x squared minus 3x over 8x squared plus 8. Okay, now remember that we had rules based on end behavior asymptotes that accorded with 3 different scenarios. This happens to be the scenario where the degree of the numerator and the degree of the denominator happen to be the same. I have a second degree, so a quadratic in the numerator, and I also have a quadratic in the denominator. And if you remember from just a few moments ago, when we have the degrees equal to each other, it winds up being the ratio of the leading coefficients, in this case 2 over 8 or 1/4. Okay? Now, the questions in terms of limits at infinity will oftentimes not be asked in that way. Okay, so sometimes they'll ask you to find the asymptotes of a particular function that you're given. And if you're asked that variety of question, and let's say that we were, instead of being asked a straight up limit question, let's say that we were asked to find the asymptotes, and in this case it's understood to be horizontal asymptotes, right? So if we're asked to find the horizontal asymptotes of this function, I actually need to ask myself 2 questions. Because I need to ask myself, what is the limit as x approaches negative infinity, as I go off the left end of the graph, of 2x squared minus 3x over 8x squared plus 8. And I need to ask myself the question that I've actually already evaluated. I need to ask myself what happens as I go off the right-hand side of the graph towards positive infinity. Okay? Now in this particular case, you actually don't have a problem. You don't have a problem because those are identical, right? When you start plugging in negative infinity, it doesn't really matter. They're the same degree, so they're going to be the same sign with increasingly large negative numbers. Because the squared gets so much larger so much faster, these start to fall out in terms of importance. The negative 3x squared, the negative 3x and the positive 8 start to become so small that they become negligible. And so basically you're just left with the ratio of 2x squared over 8x squared, which reduces to 1/4, which is why this is 1/4 and this is 1/4. Now we will actually get to problems that have sort of a quirk in them, but we won't actually do that right now. But what we will do is go ahead and run through a couple more examples on how to evaluate either when we're explicitly given the limit or when we're given a function and asked for the horizontal asymptotes. And at that point, we will, of course, evaluate both limits, both on the right-hand side of the graph and the left-hand side of the graph. So let's go ahead and do a few more. Now, let's say that we are given the limit as x approaches infinity of the cube root of x squared plus 4 over x squared minus 4. Okay, oh, sorry, I'm going to go ahead and scoot that up for you. So I have the limit as x approaches infinity of the cube root of x squared plus 4 over x squared minus 4. Now, what degree is the numerator? Well, here's the thing. When I start dealing with insanely large values of infinity, as I hinted at or sort of foreshadowed in this past example, when I told you that as x goes to negative infinity, the negative 3x and the positive 8 start to become negligible numerically, right? I have the same thing going on here. This positive 4 and this negative 4 start to become much less important when I start plugging in 10, 100, 1,000, 1,000,000, 1,000,000,000. They start to pale in comparison. So while this is not equivalent to any other expression, the limit, because you're going off to infinity, actually does wind up becoming equal to that. Now, that is easy to determine the degree of that particular numerator. It's 2/3, okay? Now, this numerator has a degree of 2/3, but functionally so does this one, okay? Now, it's not capable of being simplified, but you do have a quadratic that you are taking the cube root of. So, being able to simplify it or not, you should be able to sort of reason out the fact that the functional degree of this numerator, this whole numerator, happens to be 2/3. Well, in this case, it winds up being that first scenario underneath our three scenarios. It winds up being one in which the denominator has a larger degree than the numerator, and that limit, of course, is equal to 0. Okay? Now, like I said, the vast majority, if not all of the problems on the limits at infinity on the AP exam are inside of the multiple choice section. So, if you run into those, for the sake of everything holy, don't do them the hard way, do them the easy way. You would be amazed that when you stop, think, then do, remember that from last year? Stop, think, then do. There's actually a large number of questions on the AP exam that you can actually reason out with your Algebra 2 and pre-cal knowledge and don't actually require calculus knowledge to do. Now, even amongst those, the calculus might actually get you to the answer faster, but let's say you forget how to do a particular procedure. I have taught you a lot of things along the way where if you actually stop and reflect, you can use that previous knowledge in order to get at what you need to figure out in terms of a particular problem. Now we're coming up on about 15 minutes. I hope this has been a fruitful review of those particular things in Algebra 2 and Pre-Cal, which sort of foreshadow our discussion of limits at infinity. In the next video, maybe two, depends on how far I get and how quickly I get through, I'm going to try to do a bunch of examples, and it'll probably be two more videos, one with some moderate examples and then one where we get pretty nasty. And that way we can sort of round out our knowledge of limits at infinity and move on to the next topic. I hope that's helpful, guys.